In this video we're going to have a look at how our work on the motion of a particle in a horizontal circle can be used to model the motion of a vehicle around a bend. So, for our first example, we've got a car of mass 1200 kilograms travels around a roundabout on a horizontal circular path at a constant speed of 14 meters per second. The radius of the circle is 50 meters, and we're to assume that there is no resistance to the motion of the car and that the car can be modelled as a particle. A frictional force is directed towards the centre of the roundabout, acts on the car as it moves. We've got to find the magnitude of this force, and then we've got to show that the coefficient of friction between the car and the road must be greater than or equal to 0.4. Now we'll start by drawing a couple of diagrams. The first diagram is showing the aerial view of the car travelling around the roundabout. And then the second view, and probably the more useful view, is going to be the side-on view, looking at the car going around this circle of radius 50 meters. Now the force is acting on the car. We've got the weight of 1200 G, and we have got the normal reaction, and we've got this frictional force of magnitude F, and we've got to try and find the value of F. Now, since the car is going around in a circle, we know that there's an acceleration towards the centre of magnitude v squared over r. So applying Newton's second law towards the centre of the circle, we've got the resultant force towards the centre of the circle is simply F, must equal the mass 1200 times by v squared over r, which is the acceleration. So we've got the frictional force is 1200 times by 14 squared divided by 50, which gives us a frictional force of 4,704 newtons. Applying Newton's second law vertically, well, in the vertical direction there is no acceleration, so Newton's second law vertically just simply tells me that r minus 1200 g must equal 0. In other words, r is 1200 g, which is 11,760 newtons. For the motion to be possible, as described, we need the frictional force must be less than or equal to its maximum possible value. In other words, we must have the frictional force is less than or equal to mu times r, which means that we've got 4,704 must be less than or equal to mu times 11,760, and dividing by 11,760 gives me the required result that mu must be greater than or equal to 0.4. Now often bends are banked, and if the bend is banked, then it often will allow the car to go round the corner at a higher speed. What we're going to try and do is we're going to try and investigate this situation in a little bit more detail. As before, we're going to treat the vehicle as a particle. So there's a massive modelling assumption going on there. So let's simplify and draw a diagram. So we've got our car on a banked slope and going round a circle of radius r. The design speed for the curve is the speed of the car for there to be no tendency of the car to slip either down the banking or up the banking, so that there's no friction acting down or up the inclined plane. So that means that the forces that we've got acting are simply the weight of the object and the normal reaction of the object. In this case, the object's the car, of course. Because the car's going round in a circle of radius r, there must be an acceleration towards the centre, and that acceleration towards the centre is v squared over r. And we're assuming that v is constant, so it's a steady speed that the car is going round the bend. So, applying Newton's second law, first of all, vertically, we have the vertical component of r is going to be r cos theta, because the reaction is making an angle of theta with the vertical, as we can see in the little diagram on the left. So, resolving vertically, we've got r cos theta minus mg must equal naught. In other words, r must equal mg divided by cos theta. Applying Newton's second law towards the centre of the circle, then we've got the resultant force towards the centre is simply the component of r towards the centre of the circle, which is r sine theta, and that must equal mv squared over the radius of the motion. So we've got the reaction times sine theta equals mv squared over r. We know what the reaction is, so we can substitute for capital R. So we've got mg over cos theta times by sine theta must equal mv squared over the radius of the motion. And that in turn, when we do a little bit of simplification, gives me v squared must be the radius of the motion times by g times by tan theta. In other words, the design speed for the bend, that's the speed which has no tendency for the vehicle to slip either up or down the banking, is given by the square root of rg tan theta. Now, what happens if the car goes faster than the design speed for the curve? Well, if the car is going to go faster than the design speed for the curve, there'll be a tendency for the car to slip out of the circle. In other words, there's a tendency for the car to move up the banking. So there will be a frictional force acting down the banking, opposing that tendency to slip out of. As the speed of the car increases, this frictional force is going to increase. But we know there is a maximum possible value for the frictional force, given by F max is mu times r. So there'll be a maximum possible speed for the car, which is when the car has a tendency to slip up the slope, and the frictional force takes its maximum possible value, which is mu times r. So, looking back at our force diagram, we've got the three forces, the weight, the normal reaction and the frictional force. We know there's an acceleration towards the centre of the circle of v squared divided by the radius of the motion, and we are assuming now that the car is moving at its maximum possible speed, so that the frictional force is going to equal mu times r. So, here's our analysis of the maximum speed scenario. And we're going to start off by applying Newton's second law vertically. So we've got the component of r vertically, which is r cos theta. Take away mg. Take away the vertical component of f, which is f sine theta. So we've got r cos theta minus mg minus f sine theta must equal naught. But remember that we are assuming we're going at maximum speed, so the frictional force is taking its maximum possible value, which is mu times r. So we've got r cos theta minus mu r sine theta must equal mg. In other words, we've got r times by cos theta minus mu sine theta equals mg, which means that the reaction force is mg divided by cos theta minus mu sine theta. Applying Newton's second law towards the centre of the circle, we've now got the horizontal component of r, which is r sine theta, plus the horizontal component of f, which is f cos theta, must equal the mass times the acceleration, which is m times v squared divided by the radius. So we've got r sine theta plus f cos theta equals mv squared divided by the radius. We know f is taking its maximum value, so f is the same thing as mu r. So we've got r sine theta plus mu r cos theta equals mv squared divided by the radius. And factorising gives us r times by sine theta plus mu cos theta equals mv squared divided by the radius. But we know what the reaction force r is, so we've now got mg times by sine theta plus mu cos theta divided by cos theta minus mu sine theta must equal m times v squared divided by the radius. In other words, we have v squared equals g times the radius times by sine theta plus mu cos theta, all divided by cos theta minus mu sine theta, which gives us v max is the square root of rg times by sine theta plus mu cos theta divided by cos theta minus mu sine theta. Rather complicated expression, but at least we know what the maximum speed for the car is without it beginning to slip out of the corner. Now, to finish this little piece of work, there'll obviously be a minimum possible speed for the curve, because there's a possibility that the car will slip down the slope if it is travelling too slowly. If there's a tendency for the car to slip down the slope, then the friction will oppose that, which will mean that the frictional force is acting out of the slope, in other words, up the slope. And as an exercise now, I'd like you to find what the minimum possible speed for the car is to maintain its circular path around the bend.